All right, so what we're going to get into now is we're going to get into related rates. And related rates they're a tricky set of ideas. Oftentimes students find them to be kind of difficult, but they don't really need to be, okay? Um, they just take practice and they take a way of thinking about these kind of problems such that, you can kind of systematically, you can systematically solve them. So, on the other hand, they are also kind of tricky because they involve a lot of different applications. So we kind of have to pull from a lot of different areas in terms of like our understanding of mathematics. All right. And so consequently, we're going to be like working with a lot of triangles. We'll be working with a lot of rectangles, that sort of thing. And um, if you just keep in mind, right, basically that you're working with geometric shapes, then related rates are not necessarily the hardest things in the entire world, right? Okay. So follow along, make sure that you take the time to practice. It's really going to make a difference to practice with these things, and I think you actually should do quite well. So let's take a look. So related rate problems are real-world applications that involve the derivative of a composition of functions. In other words, they're applications of the chain rule. Okay. So let's say, for example, I take the length of a rectangle is increasing at a rate of 8 centimeters per second. Okay. Now, when I read that, what I want to get is that its length, okay, is increasing at 8 centimeters per second. So if I rewrote that, say like L, let's let L be length. So we'll let L equal the length. And so, and T is going to be time. Okay. All right. And we'll let W equal the width. All right. So one of the big things to get here is that dl dt is the change in the length over time. So dl dt is going to equal 8. Okay. And its width is increasing at a rate of 3 centimeters per second. So let's think, what would that be? Its width is increasing at a rate of 3 centimeters per second. It's a rate, so consequently, it's also going to be a derivative. It's going to be dw dt. Okay. And that's going to equal 3. When the length is 20 centimeters, so L equals 20, and the width is 10 centimeters, okay, W equals 10, how fast is the area of the rectangle increasing? Okay, so it's questions like these, right, that we're going to actually be doing when we do related rate problems. Okay, so let's say, for example, I look at something like this and I say, how fast is the area of the rectangle increasing? Well, what I need here in order to solve that is I need an equation for the area. Well, it's a rectangle. So area here is going to equal length times the width. Okay, and I want to know how fast is the area of the rectangle increasing. So I'm also looking for a rate of change. So I'm looking for dA dt. Okay, notice that every single one of my rates is a derivative. Okay, well, how do I find dA dt, right, if I've got L and W? Okay, I'm like, where the hell's T, right? Well, that's okay. That's totally fine. What we do know is that we can imagine the length and the change in the length, right, as being a function of time, and we can imagine the W as being a function of time. And so we can actually use implicit differentiation here. Okay, so this is going to be dA dt is going to equal, all right, and then we'll use the product rule, and then it's going to be L, right, or dL dt, okay, times W plus dW dt times L, okay, times L. And so consequently, all I need to do is I need to just plug in my values, okay? I'm gonna plug in my values. I get dAdt then is gonna equal 8 times 10 plus 3 times 20, okay? So that's 80 plus 60, that's 140, okay, centimeters per second. All right, we're going to see a lot more of these, but that's basically the process, right? We're going to actually be given a set of information that we'll have to use. We're going to have to probably figure out what an equation is. Okay, we'll do some differentiation, all right, and then we're going to go in and, in fact, plug in our values after we've done the differentiation. That's it. Okay. Now, does it get more complicated than that? Yes, it does. So let's actually take a look at some different things and see if we can kind of like break this down and uncomplicate it. You shouldn't get it right now. It's a little early in the process. So let's suppose that y equals the square root of 2x plus 1, where x and y are functions of t. Okay, so now, right, we're thinking, okay, x and y are functions of t, so anything that I'm doing is going to have to be with implicit differentiation. Okay, we don't actually have any t's in this, but that's okay. It's not a problem. Okay, all we're going to do is we're just going to implicitly differentiate. So anywhere I see an x, I'm going to have to make sure that I multiply that by that dx dt. Anywhere I have a y, I'm going to have to multiply by dy dt. Okay, so if I have that dx dt is equal to 3, find dy dt when x equals 4. So what I'm going to do is I'm going to notice one, I've got dx dt. I don't know, this is unknown, dy dt is an unknown. Okay, but I do have an x equals 4. All right, so after differentiation, what I should have is just an unknown dy dt, and I can solve for it. Okay, so let's first differentiate. So this is going to give me then dy dt is going to equal, okay, and then it'll be d dt times the square root of 2x, or not times the square root, d dt of the square root of 2x plus 1, okay? So in this case, we're going to have to do some chain rule, all right? We're going to let the outer function, so we'll let f of x equal the square root of t in this case, okay? And we'll call this g of, and this will be f of t, and this will be g of t, okay, is going to be 2x plus 1. All right, so f of t is going to be 1/2 t to the negative 1/2. We've seen that many, many times before. So that's f prime of t, okay? And g prime of t then is going to equal, okay, 2, right? Because that's going to be the derivative of 2 times dx dt, all right? The derivative of 2x is just 2, but then don't forget that we've actually got a function of t, not a function of x in this case, okay? So there we go. That means that this one here, so we've got dy dt is then going to equal, okay, it'll be 2 times dx dt, using the chain rule, times 1/2, okay, 2x plus 1 to the negative 1/2. Right, and that's just us using the chain rule, right? Okay, we end up, this is the derivative of 2x plus 1 with respect to t, okay? And here is the derivative of the square root of t, okay? But then we plug in the function 2x plus 1 into it, okay? All right, so now all I'm going to do, I'm actually not going to simplify here because I don't need to, okay? I'm trying to find dy dt. So dy dt is going to equal, now I'm going to take 2 times, and this is 3. This is where the 3 comes from, okay? Times, and this will be 1/2 times 2 times, and here's x equals 4. 2 times 4 plus 1 to the negative 1/2, okay? Which is equal to 2 times 3 divided by 2 times the square root of 9, okay? Which is equal to 2 times 3 divided by 2 times 3, which is equal to 1. And there we go. Done. So dy dt ends up equaling 1. Cool. So in this case, we've been given all of the function, right? And we've been given the information for the function. So what we needed to do is we needed to implicitly differentiate, okay? Utilize that chain rule to implicitly differentiate, okay? And then plug in the values that we have for, in this case, dx dt and x to get our unknown dy dt. That's going to be kind of the basic process. The challenge is to find that function, to find what y is, or to find whatever the function is that we're looking for, okay? Let's try it one more time. Now this states if dy dt equals 5, find dx dt when x equals 12. Okay, well, I already know that dy dt, okay, is going to equal 2 times dx dt times 1/2 2x plus 1 to the negative 1/2. okay? Now, what that means for us is that means that this then is, that's just simply that differential equation or the derivative that we found. Now I need to just plug in my values. dy dt now is 5. So 5 equals 2 times our unknown dx dt times 1/2, or let's just do it 1 over 2 times the square root of 2 times 12 plus 1. Okay? So this is then going to give me that 5 equals, and this is 2 over, and this will be 2 times, that's square root of 25, so 2 times 5, 2 over 2 times 5, okay, times dx dt. What we can do now is, well, this is going to be 2 over 10 or 1 over 5, okay? So this then is going to be 5 equals 1/5 times dx dt. And so that then gives me that 25 is equal to dx dt. That's it. That's the basic process. That's like the underlying process. It's basically take the derivative, right? Plug in some values, right? Just remember, right, that you're doing a lot of implicit differentiation. Okay, for related rates, you're oftentimes going to be taking the derivative with respect to something like t. You're like, where are all the t's? Well, oh, that's right. X and y are functions of t. So here's a great example of something that we'll see when we do related rates. At noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How far is the distance between the ships changing at 4 o'clock p.m.? Got it, okay? So what we have here is we have kind of like a diagram, a picture, okay? We know at noon, ship A is 150 kilometers west of ship B, okay? So here, let's take this and we're gonna make this ship A, all right? And ship A is sailing east, so here's ship B. Ship A is sailing east at 35 kilometers per hour. So what that means is, let's call this dA dt, okay? Right, the position of the ship, right, being A, dt, okay, or t being the time, so this is the rate at which the ship A is traveling. So this is going to be 35, or 35 kilometers per hour, okay? And ship B is sailing north, okay? So it's now sailing in the northern direction, all right? So dB dt is going to equal 25 kilometers per hour. Now, the thing is that right now we're not really going to worry so much about the fact that like they're moving in different directions. All right. Later on, we do multivariable calculus or working with vectors. We can really think about these different directions. Right now, let's just kind of stick with the basics. Okay. The basic rates, right? Our derivatives, rates of change. How fast is the ship sailing? Notice fast, acceleration, speed, right? Those are all derivatives, right? 35 kilometers an hour. dB dt is going to be 25 kilometers per hour. How far is the distance between the ships changing at 4 o'clock p.m.? Okay, so what we now know is that we know that, right, that ship A and ship B, well, we kind of need to figure out where ship A and ship B are going to be. So what we want to do first is we kind of want to first think about how far apart are they, because we're going to end up using the Pythagorean theorem. Okay, and we'll talk about how that kind of works. So we start out here with where they started. So this was 150 kilometers, 150 kilometers west. That's how far apart they are. Okay, then ship A starts moving east. Okay, it starts sailing east, and it does that for 4 hours. And how we know that is that we're going to go from noon to 4 o'clock p.m. So he does that for 4 hours. Okay, so what we've got here is we started out, this entire length was 150, right? But then we're going to subtract, right? This point, we want to figure out how long that line is, how far long that line is. So we're going to subtract our 4 hours times 35, okay? So it's 150 minus 4 times 30, okay? 4 times 30 is 120, and then plus another 5. Okay, so that's 140. So this is actually going to be 10 kilometers. So this distance right here is going to be 10 kilometers. That's our new distance. So we'll call this new positions. On the other hand, ship B is traveling now northward, right? So ship B is traveling northward, but we know how far it is. Now, by the way, this is clearly not drawn to scale, okay? But if it's sailing northward at 25 kilometers per hour, it's going to do that for 4 hours, okay? So this distance here is going to be 4 times 25, which equals 100, okay? Now, the distance between the two ships is this thing right here, which we can actually find, okay? We can actually find that. We'll do that in just a moment, right? But also, that's going to be, we'll call this maybe C, right? We'll call this C, right? That's the distance C. What we want to know, we want to find dc dt, okay? We want to find dc dt. So we need an equation for C so that we can then take the derivative of it, all right? And then once we've taken the derivative of dc dt, or once we've taken the derivative of C, then we can plug in our values, right? Because we actually have all of them. We have 10, we have 100, okay? We have dA dt, we have dB dt, okay? So what is a function of A and B to represent C? Well, this is one of those things where you should be really thinking to yourself, oh yeah, it's the Pythagorean theorem. Anytime I see a triangle like this, okay, and I want to draw these kind of triangles, I want to kind of make them in my mind, or I draw them on paper. You know what? I don't make them in my mind. I actually draw pictures of them. You draw a picture of it, you're like, okay, this is what it's going to look like, okay? And so C, my line, is going to equal the square root of a squared plus b squared, right? A squared plus b squared equals c squared. So C is going to equal the square root of a squared plus b squared. Awesome. So now I can take the derivative. So I'm going to move this up a little bit so I can do that. So dc dt is going to equal, okay, now I'm going to actually write this out. I'm going to do it a couple different ways. I'm going to let f of t equal the square root of t, all right? We're going to use the chain rule, and then g of t is going to equal a squared plus b squared, all right? So f prime of t, again, is going to equal 1/2 t to the negative 1/2, and then g of t is going to then equal 2a times dA dt. Okay, don't forget, we're taking the derivative with respect to t. We're going to have to use implicit differentiation. Plus 2b times dB dt. So what that gives me for dc, I'm actually going to move this so that I can get a little bit more space. dc dt is thus going to equal 2a times dA dt plus 2b times dB dt times 1 over 2 times the square root of a squared plus b squared. All right, and that's using the chain rule. So we use the chain rule with some implicit differentiation, recognizing that each one of these variables was a function of t. Okay, so now dc dt is going to equal, and I'm just going to plug in my values. Okay, I had a was equal to 10, so this is 2 times 10 times 35 plus 2 times b. B was equal to 100. If you remember, we can look back up here. It's 100. Okay, so 2 times 100 times 25 times 1 over the square root, okay, of 10 squared plus 100 squared. And now we just need to actually go out and calculate that. So dc dt is going to equal 56.7171. And that would be 71 kilometers per hour. All right. So This one, I mean, it's kind of involved, but basically if you just think to yourself, okay, I need to fill in the blanks. Okay, I need to fill in the blanks. I kind of need to think through my problem and then fill in the blanks. Let's take a look at it. All right. So we're given that at noon, the ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour. That's a rate. Ship B is sailing north at 25 kilometers an hour. That's another rate. How far is the distance between the ships changing at 4 o'clock p.m.? Well, a distance, it should tell me like kind of automatically that I'm going to use that distance formula or that I'm going to use the Pythagorean theorem. Okay, so what I want to do is I first want to imagine that starting point. I'm at 150 kilometers per hour, 150 kilometers. Okay, and ship B is basically they're kind of at a flat level with one another. Then I write in the values that I already know, my derivatives, dA dt, dB dt. Okay, and in this case, what I'm going to have to do is I'm going to have to figure out how far apart they are actually at 4 p.m. So any one of the values that I've got here for these related rates, it's going to be at the time that we're looking for its instantaneous velocity or whatever rate of change at the instant is. Okay, so I had to go out and do that. But once I did that, I had 10 here for the length for that horizontal length and 100 for that vertical length. Okay, then it was just a matter of utilizing C, right? Figuring out what C was, this function, okay? And C, we're going to use that distance function. You got to know this. It's kind of like you might as well just say, okay, you need to memorize it, right? If I'm looking for the distance between two objects, it's going to be that C value. So it's a memorize, okay? So now I have C in terms of A and B, okay? C equals the square root of A squared plus B squared, which is great because I already know A, I already know B, I know dA dt, and I know dB dt, okay? And so since I know all of those, right, all it now takes is it requires me now to go take my formula and differentiate. So I differentiated using the chain rule, okay, remembering that my function was a function of t, okay, so I had to do implicit differentiation. And then once I did that, I could just plug in my values, okay? Very process driven, but if you get the process, right, these questions get a lot easier. All right, let's try another one.